This question is a calculator problem from the free response section of an AP exam. It says here that a 12,000 liter tank is filled to capacity, and at t equals 0, the water begins to drain out, and it's modeled by the rate, R of t, measured in liters per hour, given by this piecewise function. So part A asks, is this a continuous function at t equals 5? So what we want to do is we want to see what's happening to this function as we approach it from the left-hand side and as we approach it from the right-hand side. So I'm going to let the limit as t approaches 5 from the left of 600 t over t plus 3. And when I plug in t equals 5, I get 3,000 divided by 8, and that works out to be 375. And that is liters per hour. Now I need to do the same thing from the right hand side. So it's going to be defined by this function on the right hand side. So then I check the limit as t approaches 5, now from the right hand side. And I'm going to try it in this function. So when I do that, I end up with 1,000 e to the negative 1. So 1,000 divided by e, when I work that out on my calculator, okay, that's approximately, so 1,000 divided by e, I end up with 367.89, and again that is liters per hour. And since those do not match, we can conclude that it is discontinuous at t equals 5. Part B says find the average rate at which the water is draining from the tank between t equals 0 and t equals 8. So when we talk about the average value of R, so we want to find the average value of R of t, I want to find the area under the integral of R of t. So I want the integral from 0 to 8 of R of t. And I want to divide that by the interval width, which in this case is 8 seconds. So I'm going to find the total amount of liters and divide it by 8 seconds. That gives me the average liters per, 8 hours. It'll give me the average R value of liters per hour. Now the problem is the R function is defined differently from 0 to 5 and from 5 to 8. So we're going to have to rewrite this integral and split it into two parts. So the integral in two parts is going to look like this, and I'll do different colors. So the first part is going to be the integral from 0 to 5 of 600 t over t plus 3. And then we're going to add that to the area under the curve from 5 to 8 of 1,000 e to the negative 0.2 t dt. Okay, and we cannot integrate the first one without a calculator, but we're going to do these both with a calculator anyways. Okay, so we need to know what these graphs look like. So we should have an idea what these graphs look like. So when I graph this function, from 0 to 5, it's going to look like this. And for the other part, it looks like it's going to be just slightly below, and it's going to be an exponential decay like this. So I want to find the area here in green. Okay, and again, I'm going to use my calculator to do this. And when I integrate using my calculator, I need to use the integral function on my calculator. I'm going to integrate from 0 to 5 as my upper limit. And when I do that, I get an area here of 1,234.51. That is in liters because that is the rate in time. I multiply it by time, I'm going to get liters. Then I'm going to integrate the red function here. So my lower limit is 5, my upper limit is 8. In this area, when I shade that in, this area here works out to be 829.91 liters. Okay, so then when I work out the average rate of change, it's going to be the total volume. In this case, it's going to, I'll add those two values together, so 1234.51 plus 829.91. I'm going to end up with a total volume of 2,064.42 liters, and I'm going to divide that over 8 hours, and that's going to give me an average rate of 258.05 liters per hour.